Si quieres decir algo tú. Sí. Exposición temporal.
Comprar un molde aquí con todo eso, un molde en lugar de llamado un molde para poner y así quedaría todo el bueno, porque es un modelo que tenga tapas, no porque no puedes usar esa cosa, sino que agujería lo vacío.
So new people at the institute, maybe?
Special introduce you to our Appl. He's coming. He's now an engineer. So if you want to build a board or something, please, to us. He will reading PhD studies with Christopher and myself on sitting in this role.
So we are to the diversity, we did not have yet now.
It is because of Lisbon, but also via Modal, has been working on it. It's a really important.
And before the talk today, I just wanted to remind you that today at 7 p.m., no, 7:30 p.m., right? 7:30. We have the last of the series of 3 general talks, which are in the old building of the university in downtown in Sarriera. The talk of today will be given by Emilio Hernandez Garcia on forms and forces in nature. I would like all of you to be there. I think you can learn things that you will not learn in a regular seminar here, and that you will also enjoy the talk. Emilio has promised nice pictures.
Let's continue with the seminar. Today we have Antonio Pérez to talk us about multimode dynamics.
Good afternoon to everybody. Like I said, I will talk about ring lasers and in particular in multimode dynamics of these kind of devices. And the talk is summarized as follows. First, I will talk about an introduction of the subject with a motivation. Then I will talk about the model structure of these devices. And finally, the main part of the talk, I will talk about multimode dynamics in these devices. So, ring lasers are not new. Really, they are very old. The idea of using a ring cavity to construct a laser is as old as the laser itself. The ring lasers can be classified in 2 characteristics. One is about the active medium, and the other is about the shape of the cavity. For example, here I show you a gas ring laser. Here is a photograph of another gas ring laser, a fiber ring laser, or a picture of a semiconductor ring laser. But if we talk about the shapes of the cavity, we see that in this shape is a triangular shape, or a square shape, or could be circular with new techniques of lithography. What is peculiar in these cavities are these reflections, intracavity reflections are in these cavities that couples the two electric fields that travel inside the cavity. And this is different from the usual Fabry-Perot cavities that are composed by 2 planar parallel mirrors and the light travels between them. In this type of cavities, what we have due to the interference due to the interference of the two electric fields, and what we have is a standing wave profile of the intensity. Well, more or less. It's not very good picture, but and this gives this kind of devices a rich dynamical variety, like can be a continuous wave operation, mod locking, that is a pulse operation that can be made in these devices by putting a saturated absorber inside, or by pumping in a pulser, or quick switching, that is more or less the same pulse behavior, but the mechanism is different, or we can have chaos. On the other hand, on the ring lasers, if we neglect the intercavity reflections that I mentioned above, what we have are pure traveling waves, that in contrast with these standing waves. But in real devices, what we have from these parasitic cavities that form by the intercavity reflectivities, we have a mix between the standing waves and these traveling waves. These give us, moreover, these dynamical regimes, they give us another dynamical regimes like alternate oscillations, where the two counterpropagating fields are oscillating out of phase between them, or directional instability, where one of the fields has an intensity bigger than the other, and we can switch between these two directions of emission. As example, I show you here a scheme of a fiber ring laser. In this case, they put, from this paper, they put a polarizer isolator to make the device to emit in one direction only. And what they found in this, I show you in this Li curve, where this plot the out power versus the pump power, they found different regimes, like first a continuous wave regime, then a single pulse, that is here depicted, because here is plotted only the average of the pulse, and multiple pulse. As another example, I want to show you what a semiconductor ring laser was done in this paper. Well, here, I show you the structure of this semiconductor ring laser. I will talk later about the details of the structure, but what we have to think about is that here there are two photodetectors that detect the two modes independently, and here a third photodetector that detects the total intensity of the field, of the two fields. Then we can understand this Li curve, where is the current of the photodetectors versus the ring current. We can see that above the threshold, when the laser is on, this device emits in bidirectional continuous wave. That means that the two emissions, the two electric fields are present and have the same intensity. Then we go to a bidirectional alternate oscillations that I commented before, and here you can see a time trace from the oscilloscope, because here, as another time, there is the average, this energy. And third one that is called the unidirectional regime, where one of the components of the field has a greater intensity than the other, and this can be switched and can be exploited, as we are going to see.
Sorry, what is PD3?
This is the total intensity. This photodetector detects all the intensity in the two directions of polarization. But if you have any question, then
We can go back. In the last regime, PD1 is essentially zero. And PD3 should be the addition of PD1 and PD2?
Yes, it should be. Yes. Well, but the thing is also that, for example, here PD3 is integrated in the waveguide, and the other photodetectors have to, the light has to come out from the structure.
The scale for the PD2 or PD1.
Okay, it's
just for.
well, but
just the evanescently coupled energy, while the other one is.
yes, here and here is more, but yes, it's multiplied by a factor here.
So it's even less.
The radius is 1 millimeter?
In this case, it's 1 millimeter. But well, I will show you about other more smaller devices. Well, this device has a traditional application that is the gyroscope. A gyroscope is an apparatus for rotation sensing that explodes the Sachs-Nat effect, that when a cavity is rotated, there is a difference in wavelength that comes from the fact that the two electric fields have different optical paths. And then we can measure this difference in wavelength, and we can then take the rotation. And here I show you a commercial device with the 3 dimensions that it perhaps is for a plane or a very expensive car. And a new application is an optical memory that exploits this directional stability that I commented before and was demonstrated in this paper not a long time ago. These devices are usually modeled by rate equation.
Again, how does it work as a memory?
How does it work? Well, it's like the principle of a transistor, or not, but now it's in the direction of emission. We can have 2 states.
And has the same advantage?
For the moment. well, it's all optical. We have no change between electronical and optical. It could be nice in the future.
How do they switch between the 2 directions?
Well, you switch between, for example, see here is rotating in the field, you can inject light in this direction, and then if depending on the energy of the pulse or the frequency, then it jumps. Well, and then these models, these devices are usually modeled with rate equations model that are system of ordinary differential equations, where the spatial effects are written in a mean field approximation, and usually they made the adiabatic elimination of the polarization. This comes from the processes in a laser that is a fight, well, it's not a fight, but between different processes and different time scales, between the electric fields, the polarization, and the population difference. Usually in rate equations, what they make is that this time scale is neglected, approximated, and then we only return these 2 time scales. Usually they are single mode, but it can be multi-mode, and they are relatively have a low computational cost if we compare it with traveling wave models that are based in partial differential equations. Then in these models we have the spatial effects totally retained. The multimode behavior arrives naturally in these models, and the problem is that the computational cost is higher than in the equation model. Here I show you some examples of rate equations models for ring lasers, and here traveling wave models for Fabry-Perot and ring lasers. And well, to conclude this introduction, I put these objectives that I will study spatio-temporal dynamics in ring lasers by means of construct a model that retains the special effects and the coupling between the different longitudinal modes will be a traveling wave model, And finally, to develop one tool to study different problems, like for example the one who will treat here, multimode dynamics, or different optical cavities, directional switching, mode locking, etc.
What is one, sorry?
One.
There is one tool, okay.
Yes, it's one tool. Well, so let's go to the second part of the talk. Is summarized, like, first I will recall you the Fabry-Perot modes of a cavity, then I will talk about a ring resonator and its modes, and I will compare with the Fabry-Perot, and finally I will talk about a real device that is a semiconductor ring laser with output waveguides, and this work was published in IFISC letters last year. Well, I think that all of you know this, but I will repeat it. A Fabry-Perot cavity, I said before, that is composed by two planar parallel mirrors and the light travels on it. Inside it, we can write the electric field in this way by decomposing the electric field in the two propagation directions and in the Fourier space, where Q is the wave number of the field of the wave. Then we apply the boundary conditions. For example, for the forward field, at 0 point is the reflected part of the backward field at 0 point, and the same for the L point. It's not. Then this system of equations, we can solve it for the wave number, and we obtain the real part that are the modes of the cavity, and the imaginary part that are the losses of the cavity. We have infinite solutions. And what happens in a ring? Well, we can think in the simple ring that is composed by a waveguide and a spatial point that is characterized by a transmission and a reflection coefficient. In the same way, we write the electric field in the same way, but now the boundary conditions are different. There is a part that is transmitted and another that is reflected. For example, for the forward field, at the 0 point, there is one part that comes from the reflection of the backward field at 0 point, and the other from the transmitted of the forward field at the point L. Then, if we think that this point we have the reflection coefficient equal to 0 and the transmittivity equal to 1, we have a real wave number, we don't have losses, and it's what we call the ideal ring. On the other hand, if we think that RMT can be different of 0, what we obtain is a wave number that has two families of solutions. And well, to get more physical insight, I will talk about this point without any losses, to try to compare it with the Fabry-Perot. And then if suppose there is no losses, from every textbook in optics we can find this conservation law and this reciprocity condition, and then we can write this T plus minus R, the modulus of T plus minus R is equal to 1. Then we can write it in a complex exponential form with a phase theta plus minus that can be written in one or the other of these coefficients. In this case, I write it with R, with the reflection coefficient. Then the modes are written like that. We can see that if the reflection is complex, then if the reflection is real, then this term disappears, and what we have is a splitting between the ideal modes. There is a difference from one branch to another. If it's complex, in general, what we have, moreover, the splitting is a displacement. And we can see that in this plot I show you, I plot the reflection coefficient and the wave number normalized, and we can see that at 0, what we have is an ideal ring. And when we put the R equal to 1, what we obtain are the modes of a Fabry-Perot cavity. In the middle is what a ring is really, and is the region where we are going to study these kind of devices. So I present you the real device. The real device is a circular waveguide of 2 microns, like I put here a transversal code. These are 2 microns wide, and is coupled to 2 output waveguides via a evanescent point coupler here. And the experiment consists in inject light from a tunable laser at port 1 and see what goes out at port 3 and port 4. The laser is biased close to threshold in order to obtain the transfer function of this structure while we are scanning in wavelength from the tunable laser. Well, this experiment was performed by S.Fürst at the Glasgow University, and what they obtained was at port 3 a doublet structure, and at port 4 the same doublet structure, but instead of having peaks in these plots, they show dips. Here I put you 2 arrows that represent the ideal ring modes that I told before. And moreover, they note that this difference between these 2 peaks are not constant, like I showed you in the previous case.
What does it mean, the negative values with respect to what?
Well, this comes from, well, you are, well, I will tell you in the next slide, but this comes because we are injecting a slight gain in order to take the device close to the transparency index. This is the background of a spontaneous emission. Well, as I was telling, the difference between these doublets is not constant, and we can see here that here I plotted the ideal ring modes in wavelength, and here the detuning becomes for this difference, and we can see that there is a modulation. From the theoretical point of view, that's what we do. We model the device with six waveguides and their corresponding counter-propagating fields. Also, we put as the ports of output and input, we put some reflections. We also model the coupling between the output waveguides and the ring by 2 evanescent couplers that are lossless, they are the same, and they introduce a small reflectivity due to the point character. But, okay, from here then we apply boundary conditions and we have a system of 12 equations to solve, but well, we can make it in a resumed way.
So what do you mean by the point character?
Oh, because when you... Okay, because there is there are 2 waveguides, then in this region the refraction index changes, and then
changes. This is there is the fiber. So the horizontal thing. What is this? A fiber? Is a linear device? A normal thing?
Well, it's semiconductor, but it's not common.
Okay, so the material changes, even the coupler changes the.
Yes, for the change or. But well, it's small. It's very small. Then, well, for notation purpose, I write this system in this other system with 2 special points with different transmission and reflection coefficients that now they depend on the frequency, and we can write a round trip condition that depends on these coefficients and these frequencies and lengths of these output waveguides, and we can write the modes. And well, here I write it, the transfer function for port 3, and we can see that it's in very good agreement. But we don't get these dips because we don't include the spontaneous emission noise in our analysis. But we can talk about it. We note, well, the people from the University of Glasgow note that these dips depends on the current that the laser has. And these currents, well, Emilio almost said before that when we don't inject light at port 1, what comes out at port 3 and port 4 comes directly from the spontaneous emission, that due to the slight gain that we are putting in the laser. But when we are injecting light at port 1, some of these carriers that will give us the spontaneous emission are favored with, depending on the frequency, because this structure acts like a filter. Depending on this injected light, burns out the carriers and produce a stimulated emission. Then the spontaneous emission is suppressed, and we can note it in this port. In this node becomes the light injected will travel almost directly. And well, about the splitting of the modes, we can rate it in this way, where we introduce the alpha, that is the enhancement line width factor, and we know that we recover the fast modulation, there are almost three modes, and that is due to the output wavelengths, the length and the reflectivities, and these output wavelengths, and a small modulation that comes from this small reflectivity or residual reflectivity at the couplers. Well, the conclusion for this part is that we have experimentally studied the modal structure by measuring of a semiconductor ring laser, by measuring the transfer function properties of the device biased close to threshold, and we know that the residual reflectivities in the light extraction sections determine the frequency splitting between the two branches of solutions, and these facts are determine the full cavity properties of the ring lasers and possibly affect the dynamics of these devices. So
you have said that you have a theory reproduces the data. I see it reproduces the splitting between the nodes. You are not interested in the amplitude, the intensity of the nodes?
In the amplitude, you say in this amplitude?
The right dot
yes, but
outlet is different in the
yes, but these measures are very fine measures. It's very difficult to say really if this point here is good or not. It's difficult. Then
so you don't believe this? You believe that splitting between the
yes, more than intensity of.
And the scale, the theoretical graph is arbitrary or?
Well, again?
Yeah, 0.2, 0.3, and in the left it's
yes.
much smaller.
No, here is only less. No, less. In the other one, no. In this case, we put the numbers in the right way, and we obtain more or less the same numbers. So then I will move to the main part of the talk, that is about multimode dynamics in these devices. First I will talk about the model, I will present you the model, some analytical results, and some tests that we perform to assure the correctness and the accuracy of the numerical implementation. Then I will talk about two cases, interesting cases for multimode dynamics, that moderate gain bandwidth and less gain bandwidth. This work was recently submitted to Physical Review. And finally, we talk about another geometries, and in particular about a Snail laser. That is a work that we are preparing with people from Glasgow and Brussels. So I will talk to you about the model. the model is written in a semi-classical approach. It means that the electric fields are described with the classical theory of Maxwell and wave equations, and the medium is described by a quantum mechanical way. We perform the slowly varying amplitude approximation both in time and space for the electric fields, retaining only the slow modulation, well, the slow dynamics, and we made it for the simplest case of a two-level atom by putting a two-level atom where the transition energy is described with this atomic frequency, that's omega A, and we put an interaction Hamiltonian in the dipole approximation. This is a normal procedure that you can find in these two books. We also retain the correction to the first order to a population difference grating induced by the propagating fields. I know that more you don't know about this, but, well, in the presence of two counter-propagating fields, in the space, the carriers are born in different ways. Where the intensity is bigger, the carriers are bound less than when the intensity is higher. And this acts like a black mirror. It's a source of coupling between the two counter-propagating waves. And we return it to the first order. And finally, we model the spontaneous emission like white Gaussian noise as polarization sources, and that are independent from time and space for each point of the cavity. So the model reads like that: two partial differential equations for the electric fields, A plus and minus. Now I change forward for plus and backward for minus, and that depends on the polarization of the medium in this direction, B plus minus, and in this alpha there are the internal losses of the cavity. The polarization has this shape, well, this form, where there is a term of decay that comes with detuning, that I will talk in the next slide more details about this detuning and this gamma, that is the gain pure bandwidth. There is a term of gain and the term of the spontaneous emission that comes with a beta, that is a coefficient of intensity, and is depends on the instantaneous value of the population difference, and the equations for the different contributions to the population difference, where J is the pump, there is a decay term, a diffusion term, the stimulated emission term, and here for the second contribution to this grating, there is a decay term that depends on this decay of the population difference and the diffusion, and another term of stimulated emission. What we do at this point is to neglect the diffusion in this equation, and we retain the effect of the diffusion here in the grating terms. Then, to close the problem, we apply boundary conditions that in this case are written in general for different transmission and reflection coefficient going from one point to another, but in the next I will consider only a transmission and a reflection coefficient. Also we put this term that comes from the frequency, carrier frequency, optical carrier frequency. We put equal to 1, and then this optical carrier frequency means that we have the frequency in one mode of the cavity, like I showed you here. There is the modes of the cavity, and this is the carrier frequency. And what is the detuning? The detuning is the difference between this carrier frequency and the atomic frequency. And the gain curve bandwidth is this bandwidth. So then, well, this model is clearly non-linear, but there are some things that we can do it analytically. And for example, we can calculate the laser threshold and the frequencies at threshold by making a linear stability analysis of the off solution. The off solution is where all the electric fields are not present. And we arrive to these equations, and we know that we have another time these two branches of solutions. It's always there are two branches of solutions. We can plot it, and we see the difference. And we can see that, for example, for this parameter choice, we have the lowest threshold at mode 2. And if we perform a Taylor expansion of these two equations, what we found is that for a small values of R, is more or less linear with R. Then we can see, but well, here is a big difference. So this, in order to check the accuracy of our numerical implementation, this was the first test we made to obtain our analytical results, and then we take this paper from the late 80s that talks about the stability of the bidirectional ring laser operation. In this paper, well, they use a rate equation approximation, but they retain this carrier gating by a mean field approximation, and well, we have to make a translation between the two. We make a translation between this parameter choice and our parameter choice to obtain the things more or less like they obtain. This is from the paper, and these are our simulations. And moreover, in this paper, they don't include any reflection. We included a small reflection, and we include noise. And in this paper, they don't include noise and reflection, and we can see that the behavior is very similar. In this paper, also, what they did was to characterize the stability of these solutions in front of the detuning and the pump of the laser. And we also check these properties. We go from an unstable region, and we fixing the current and scanning the tuning, we go to a chaotic behavior. And if we can go from the unstable region to the stable region, like I showed you here, where the two colors are the two counterpropagating fields. So now that we are assured that our numerical implementation of the model is fine, then let's play with it. So we want to we want to study multimode dynamics, and to favor it, what we did is to put the atomic frequency in the middle of the two modes. Then these two modes have the same threshold. This I study the dependence on the detuning and the gain curve bandwidth, because these are the relevant things for the multimode dynamics. And what I obtained for moderate gain bandwidth, I will show you in this Li curve, but I will tell you there are two different colors that correspond to the two different electric fields, and different figures to the maximum and the minimum of every field. Then, for example, here, after the threshold, what we have is that two fields are emitting in the same intensity, but they are oscillating. And then, at one point, one of the electric fields is suppressed, and the other one is still maintaining these oscillations. If we go further in current, we continue in this regime, but suddenly it's a smooth transition, but we go to another regime where the two counter-aggregating fields have the same intensity. Well, here I show you.
When you say that this is smooth?
Well, here you cannot see if it's smooth, but I made another simulations and it's smooth. Well, here I show you the spectrum and the time trace for this case when I was scanning in pump for higher pump, and suddenly it changed and the laser begins to emit every propagation intensity in a different mode. It goes from almost unidirectional emission in a big number of modes to emitting in two modes, one for each direction of emission.
I would like to know the scale of the status, because 10 power 5.
Sorry?
What is the meaning of 10 power 5?
Well, it's really, it's to compare only. No, there are no units, it's arbitrary units. But it's in local scale. If you are telling
because what I guess is that 10 power 5 in dB is something like.
Oh no, yes, no, but we are not. I'm not treating with real numbers. My model is dimensionless, and I put all. There are no dimensions here. Here I put dimensions, but only for make a clear graph. But I am dealing with a real laser of 1 meter long with this separation between the modes. But this can be changed.
In a real issue, what is the input power of this laser?
Sorry?
In real issue, what is the input power that you use?
What is the milliwatts, more or less, in semiconductor? But here I am talking about general lasers. I am not talking about a specific kind of laser.
What I'm not understanding is that if you have, for instance, 10 million watts, for instance, and then you scale in order to have 10 power 5 as the spectrum in dB. I don't know.
But they are not dBs. It's only arbitrary. Perhaps the 0 dB is here. I don't know. Then, okay, we have, and these dynamical regimes can be interchanging in the direction emission. Then we have multi-stability in different, in the same parameter choice and in the same values of current. So if we move just a bit the tuning, the landscape change. Near threshold, what we obtain now is a single mode of direction and bidirectional. At one point, then one of the fields is suppressed and the other one continues emitting in single mode. Since it arrives at one point where the other field is switched on and is switched on the other mode. And then the two electric fields are switched on, but they have different intensity and, well, this small comes from the contributions to the different modes. And also, if we change the initial condition at this point, for example, if we favor the unidirectional, we favor the directional emission by putting an initial condition unidirectional, what we obtain is a completely different scenario that remembers the previous slide, that is an oscillation of one of the modes and the other is completely sparse. Once again, we have multi-stability in this system. If we decrease more the detuning, we have single mode operation and nothing more. But now I move to the large gain bandwidth, then now it's more wider and can happen a lot of things different. But we are now in the middle between the two modes. We are in the same case that at the beginning. Then at threshold, once again the two modes are present, the two electric fields, and are oscillating. At one point, the oscillations become a very small difference that comes from the fact that one mode is taken by one direction and the other by the other. So if we increase the palm, what we obtain are a new dynamical regime that is like the alternate oscillations that I showed you before. And if we increase the palm, what we obtain is a unidirectional regime that comes here, but we know that the other suppressed field is beginning to start to lace. And what is curious is that it's not beginning to start to lace in the next mode, but in the other. There are two modes different. And here we have the same behavior as before with the two intensities different. So if we change the tuning, what we obtain are more or less near threshold the same behavior. One of the modes are suppressed, the other not, and finally it is a single mode operation. But at one point, this single mode operation turns to a mode logging regime where a plenty of modes contribute to this cruise emission. So I was using an object-oriented language, and then I realized that we can make it, we can have this one tool, because we can write discretized elements and construct every geometry that we want. We can write, for example, with these three elements, a waveguide, a point with transmission and reflection, or a coupler with an efficiency. We can write, we can have different cavities like a Fabry-Perot, a ring with output waveguide, coupled rings, and what do you want? And then what we made first was to characterize this device. It's a Snail laser. That the difference with the ring is how the connections in this coupler are made. And also, the only waveguide that is found is this very big one. The others, this reflection coefficient is very high to enhance the emission in this direction. Then, from the experimental point of view, what they obtain are these curves, these LL curves, for the ring current versus the optical power, for different values of this coupling between these two waveguides. And we can see that for higher coupling efficiencies, the threshold goes down, and the slope in this Li curve goes down also. This was the first thing we did with this model, with the element discretized, and we obtained the same behavior for the threshold and the slope of the cavity. So that's all. The conclusions. We studied multimode dynamics of a two-level ring laser using a bidirectional timing wave model. The model and its numerical implementation have been tested by reproducing the analytical and analytical results and the dynamical results obtained in the single mode limit by the data I commented. And we found as far as we know, another dynamical regimes where the two electric fields emit at different wavelengths. And also, we reported mod-locking unidirectional emission without introducing any cavity, any additional element that favors the curious operation, like is due. And we extend our model to simulate different laser cavities and Appl. Thank you.
Okay, any questions already, but any other comments or questions? Maybe?
This model is not for semiconductor lasers, but for any ring laser. But has been made lasering built since in 40 years. So there are experimental results showing this.
No, I found some experimental results about.
The Snail is new, but the other
Yes.
the classical rings.
Yes, I found some results, experimental results, with this kind of behavior, that the intensities have different intensity. But in these papers, there are very old papers, they don't make the spectrum, and we don't know about if they are a single mode or not.
At the beginning you say that there are like two methods, one with ordinary differential equations and the other with partial differential equations. What do you miss by using this method instead of the other?
What do you miss? Well,
is there this is the question.
Yes, this is the partial differential equation. Then we are retaining all the time scales that I plotted before. I don't know if and the other is an approximation by red, or approximations also.
Because they have complementary information.
Well, from this model we can go to the other model, but no vice versa. Yes, because we retain the spatial effects explicitly.
I don't know if I missed something. In the first part, you were showing this splitting, and the analytical calculation was just linear, was just guides with mirrors.
Yes, only transfer function of the cavity.
Okay, but then in the experiment, you were mentioning that they were needing to introduce some gain to observe this. Why they? I mean, this should be just something given by the structure of the.
Yes, but well, because I suppose that for the absorption of the material, that if you inject light, it will be not transparent, really transparent. It will absorb the light that you inject, and then they put it near the threshold or near transparency for this to can achieve to see the light that comes out. Because we suppose that these small devices have more losses than what we take.
So just a matter of the sensitivity of the detector.
Yes.
Those questions. I have a question. I don't know if it is simple or difficult. You've shown us many results on different geometries, different situations, and so on. Now, what is the general question that you address?
What is the general question?
What is the question?
Well, I was.
Why are you doing this?
Well, because I was trying to know or to explore what are the dynamics when we talk about different modes and the competition between them. And well, this is a beginning.
But this is not a new question.
No.
What's new in the question?
Well, what is new is these things are not in papers for a ring lasers, because the new thing here is the unidirectional thing of this model. Usually in the unidirectional ring lasers.
So that last question.
And just a curiosity, the snail thing that you showed again, if you unfold it in a linear Fabry-Perot or not Fabry-Perot,
well, it has.
What is the difference?
Well,
is in the box?
Okay, this. Okay, for half a Fabry-Perot from this device, the coupling between this and this waveguide has to be zero. Then what we have.
There is a coupling between these two. Okay.
Yes, and if the coupling is of 100%, what we obtain are a ring and a Fabry-Perot independent. But we are in a mid situation.
It would be completely different from the case, for instance, you have one Fabry-Perot inside another Fabry-Perot or things like this.
Well, these are things of corporate capital. I don't think that it's the same, but it's similar.
Okay, so let's have corporate science.
No, porque está dando ganancias. Oye, una curiosidad que es la